presentation by Team5. In this presentation, we will provide one potential scenario application of the air filtration technology, identify two technological performance improvements necessary to make our application possible, and with the ultimate aim in contributing to one of the Sustainable Development Goals of by 2030 substantially reducing the number of deaths and illnesses from outdoor particulate air pollution in Asian cities. The World Health Organization reported in 2012 that approximately 7 million people around the world died as a result of air pollution exposure. The difficulty in reducing air pollution comes from the fact that effective pollution control requires increased collaboration across professions, industries, and cities. Collaborative efforts are required in areas such as social, technological, economic, environmental, and political.
By understanding the technological breakthroughs that now make up the 2015 filter technology, which are shown on the timeline, we can get a grip of the main characteristics to focus on to improve the performance of our filter technology, and we have listed a key performance indicator here. Given Blue Air, a Swedish air purifier filter company, as a starting point for this task, we have identified the main weaknesses of the well-known HEPA high-quality filter. Firstly, it is the cost of having a short product lifespan that causes costly replacement of 100 per air purifier per year. If assuming that we could extend the life of the HEPA silent to 1 year by improving the quality of the filter, we could see a cost reduction of $300 yearly. Secondly, another main weakness is that HEPA filter can only remove 99.97% of particles in the air down to 0.3 microns in size. But knowing that 90% of particles are smaller than this, called ultrafine particles, these filters themselves does not actually solve the problem, as it is marketed by profit-driven companies. In terms of potential new application for the technological improvements, it obviously boils down to the economic viability of such an application. We first sought to implement HEPA filters in cars' already existing air conditioning systems, but we then asked ourselves who will want to pay for this. We realized quite quickly that the barrier, the high cost of adding this filter to a car in the manufacturing process, was way too high, and so after doing a quick cost-benefit analysis, we decided to narrow down to public transportation only, and more explicitly subway trains located in Beijing, China, assuming that governments are more willing to take on this cost. Why is this true? Firstly, generally speaking, governments should have more capital to play around with in the transportation budget to create value for the common good compared to profit-driven car manufacturers. Secondly, also from the incentive of healthcare cost savings in the long term caused by indoor air pollution, governments become a more realistic source of capital for implementing HEPA filters in subway existing ventilation systems. By this, we know that we have targeted the right application for this technology.
As we choose to focus on the air quality of public transportation in China, we further decided to choose the rail transit systems in Beijing as a starting point for our scenario. The reason that we choose subway system is mainly because of the proved bad air quality inside of the subway. A non-government organization did a research about air quality inside of the Beijing subway system and reported that PM 2.5 value reached 72 in the carriage and 129 on the subway platform, while the offset index is only 8. This means air quality could be up to 16 times worse in the subway system than outside. According to a study by King's College, the main source of the bad air quality inside of the subway comes from dust particles, which are generated when subway tracks and wheels clash together. Those particles contain metal and could be extremely harmful for human respiratory and nervous systems. Moreover, choosing Beijing as a starting point is because its scale and influence. Firstly, we ran a quick search showing that China and Beijing ranked the top 1 and 2 in terms of social sharing about air pollution problem. Secondly, Beijing subway has the highest ridership in the world, with 3.41 billion trips delivered in 2014. And it is estimated that the size in terms of length of the whole system is going to be doubled by 2020 compared with 2014. Also, in terms of commuting time, BBC found the average time that a commuter would spend in transportation in Beijing reached 52 minutes, which is the longest in China, and it is even worse than in New York. That means a massive number of riders in Beijing are spending a considerably large amount of time in subway. Furthermore, several cases has been reported that some frequent subway riders in Beijing were having lung and brain problems, potentially because of the bad air quality inside of Beijing subway system. Therefore, improving the air quality in Beijing subway can potentially reduce the exposure and illness for a large amount of riders. and we want to deal with this problem more efficiently by applying new technologies that has been developing and installing the high-quality air purifier filter inside of all 3,400 subway carriages in Beijing.
We now look closely at how we can reduce the air pollution inside the trains. In this cross-section view of the carriage, the yellow arrow shows the dirty air being pushed into the roof compartment, the red arrow shows some of the air which is released outside, and the blue arrow shows the conditioned air which went through the air conditioners that are placed just above the ceiling. This figure shows the configuration of the car monitoring system for a typical train such as the Tube Line 5, which runs through the city of Beijing. The system shows a range of electronic devices on the train in each carriage, and it shows if the ventilation units are working or not. There are 2 ventilation units per carriage. Air conditioners already have replaceable filters built in, which removes large particles from the air such as visible dust. We have 2 examples here of where the filters are in air conditioners and what it looks like. We can do more with air filtration technology by replacing the existing low-quality air filters with advanced air purification filters specifically designed to purify air and reduce the level of small particles in the air which are size PM2.5 or smaller.
As Anna said earlier, the HEPA filters are actually not as brilliant as they sound at first glance, and they are not successful at removing ultrafine particles. The next stage up is the ULPA filters, which are able to remove 99.99% of particles down to 0.1 microns in size. But it is this last segment of particles, which is 0.1 microns and smaller, that actually make up 90% of all particles in the air, which we want to be more successful at removing. Having done some analysis, we came down to 3 technologies that work to remove ultrafine particles below this boundary of 0.1 microns in size. These are UV, ionic, and activated carbon. We chose to look at activated carbon in particular as UV produces ozone, which is harmful to human health, and ionic filtering systems are not as efficient at retaining the particles that they filter. To give you an idea of how activated carbon works as an air filtering technique, carbon is treated with oxygen, which produces a highly porous material providing a large surface area. It is this which gives activated carbon its unique absorption properties. The process creates a very large internal surface area. The more surface area, the more the carbon can absorb. The activated carbon pores can be as small as 0.02 microns in diameter, and this allows it to remove the tiniest of particles, including volatile organic compounds. Sometimes the carbon is treated with oxygen and another chemical, often potassium. This creates a chemisorbent, which is better at removing inorganic gases and gases that are highly chemically reactive. Activated carbon works by adsorption. In this process, the gas bonds to the surface of the activated carbon, thus letting the clean air flow out of the other side of the filter. Due to the large internal surface area of activated carbon, it can actually absorb up to 60% of its weight. Good carbon filters of 10 pounds or more, depending on the environment in which they are used, can last anywhere from up to 5 years before all the pores are full, and then it would just be a case of removing the activated carbon layer and slotting in a new one. We recommend using 2 layers of activated carbon at different stages in the air purifying unit. For example, here we have 1 layer between the pre-filter and the HEPA filter and 1 at the end. This is a sort of double check, if you like, that as many ultrafine particles have been adsorbed and won't be released back into the air. So what's so great about activated carbon as an air purifying material? Well, it can absorb 60% of its weight in airborne pollutants. The more activated carbon in the filter, the more pollutants it can remove and the longer the filter lasts. It's cheap and also light. A study done by ResearchGate found that there are on average 2.49 times 10 to the 10 ultrafine particles per cubic metre of air in Beijing. We combine this with the volume of Beijing subway carriages, which is 101.4 metres cubed, and with some simple calculations we were able to conclude that in the best case scenario, if the activated carbon only absorbed the ultrafine particles in the air, which is not a far off assumption as it is less effective at collecting the larger particles, this is where the HEPA filter stage works best. Then just 1 pound of activated carbon in a filter could adsorb close to 6 million times the volume of ultrafine particles in one Beijing subway carriage. Considering that also the average number of riders daily in Beijing as of 2014 was 9.28 million, these filters have the ability to have a positive and significant impact on the health of these commuters every day.
After doing a detailed patent analysis on QUID, we found a recent patent filing from China which presents a specific activated carbon filter material useful for air conditioner filters and air purification devices. So we believe the technology is just emerging, but already it's been considered for use directly related to our application of air conditioners.
Knowing how high the cost of replacement is, in order to successfully realize the integration of filter in the Beijing subways, we need to maximize the cost effectiveness when replacing the filters in the air conditioning systems. From previous analysis, we know that the lifespan of HEPA filters is determined by its design and materials. The common material used is glass filter, which is too fragile for this potential application, hence making up a critical technological constraint. So which material layout should we then use? By looking at the study done in Seoul, Korea, that measure the environmental benefits against the cost of filter renovation in subway ventilation systems, we could draw some important conclusions. We can clearly see that the combined filters material layout is significantly having a greater positive environmental effect. The table clearly demonstrates the social benefit on combined filters in contrast to choosing only a pre-filter layout. This extra layer will collect 4.05 kilograms more PM2.5 in trains per year and also minimize the environmental cost by $1,322 per year. But is this combined filter setup of economically viable investment? Run some numbers. This study replaced the pre-filter twice a month and cost $252 each time, so that the annual cost becomes $6,048. The actual expense for combined filter layout is $6,000 for the first test installation plus the replacement cost every 3 months of $450. In the long run, the new combined filtration layout costs approximately $8,756 per year, including filter disposal, labor charge, and the equipment depreciation cost for 20 years. So, to answer the question of cost effectiveness by extending product lifespan of filter, which is basically a material choice, if we consider the metrics of overall effect achieved from the investment of each material, we can see that the conventional pre-filter layout is the same as the combined filter layout, more exact 41%. How is this then possible when combined layout lowers the social cost significantly? Simply because the cost of combined materials is higher compared to the pre-filter per year only, so it makes the effectiveness of the investment a bit handicapped. But this said, if we increase the current investment efficiency of 41% to go beyond the pre-filter only return on investment, then we create value both in economical and environmental incentive for the Chinese government to act and invest in this application. So to conclude, this is the performance gap that we need to achieve to make this application economically viable, making the social benefit override the cost element. Now, with the technological targets of 1, making sure that our filters capture smaller particles, and 2, increase the cost effectiveness of filter replacements in mind, how will this application ultimately help us reach the Sustainable Development Goals after all? Let's now imagine Lucy. She's a Beijing citizen and spends an average of 52 minutes commuting to work every day, which is approximately 60 kilometers of travel. The in-train concentration exposure in Beijing is 112.6 PM2.5, which in comparison to other cities worldwide is at an extremely harmful level. Studies show that commuting in the subway attributes substantially to the personal exposure. For example, the study In-Train Quality Assessment of the Railway Transit System in Beijing highlights that better ventilation system is one of the most significant factors in assessing the in-train air quality, which proves our point of providing a solution to apply more efficient air purifying filters on existing air conditioners. By cleaning the background air in carriages, using this improved pre-filters and can capture both PM2.5 and smaller particles, studies show that we would be able to reduce the total negative health impact of Lucy's daily commute with significant health benefits, such as longer life, etc. Also, knowing that Lucy is one amongst an average of 9.2786 million subway travels per day in Beijing, with peak single-day ridership reaching up to 11.5 million in Beijing, the potential health benefits associated with less exposure every day is huge. Several previous studies reveal that the commuter exposure to traffic-related pollutants is greatly influenced by the choice of commuting, and if we can improve the conditions for the millions of people that are commuting via subway every day, we can ultimately reach the Sustainable Development Goals at scale. In summary and advice to UK CDS, we would like them to make our application of reducing in-train air pollution possible by 1, funding products to improve air filtration technology to capture smaller, more harmful particles, 2, funding products to increase the cost effectiveness of air purifier filters, with the ultimate aim of achieving the CDGs. As our technological application is designed to ultimately convert standard air conditioners to particulate matter filtration devices, the application scenario could be endless. Depending on the result of the test implementation of Beijing Trins, the next scenario would be the train station, buses, schools, offices, and other locations where there is an existing air conditioner actively in use. Therefore, the benefits from this technological improvement in reducing the number of deaths from particular air pollution could be far greater than our initial estimate.